Okay, here we go. Okay, so just continuing on with this, hopefully it will take maybe 20, 25 minutes more and then I'm done. So we're going to continue on. The reason why I call this section Gaussian Discriminant Functions is because we are assuming that all the features are Gaussian distributed. So we're able to discriminate between one class and another by Gaussian discriminant functions. So we can say that the decision boundary is when the choice is equiprobable, right? So you know what the decision rule was: when one probability is higher than another, that's the class you choose. So if we were to find all the points where both of the probabilities were equal, you can consider that to be a decision boundary, right? Because anything slightly larger will mean that you go to one class, and anything slightly smaller will mean you go to another class. So the point where all the probabilities are equal, the line that defines them, you can consider that to be a decision boundary, right? Because anything on one side is one class, anything on the other side another class, and then everything that is equal probability is along that line. Okay? So the decision boundary is when the choice is equiprobable. So you want to find when the posteriors are equal. Okay? So you want to find every single value of x that will satisfy the above condition. Okay? So what we're going to do is we're going to define what's known as a discriminant function, which is called g sub I. So the discriminant function for class I is just simply the posterior probability. So g sub I x is just the posterior probability, right? We got rid of the evidence because when you're comparing them both, the p of x is canceled. So this is just for both classes, and this is the decision boundary. Okay? So all you have to do is just solve for every value of x that makes this equal, and that will give you your decision boundary. It's actually quite nice. All right? So since this is Gaussian, what I like to do is I like to take the log of both sides because it gets rid of the exponential. So since discriminants are Gaussian, we can take the log of both sides. It makes it easier, okay, for solving stuff. So we can take the log of both sides. Okay? And what we can do now, so therefore, right, it would just be, so if you were to take the log of this, it would just, when you take the log of products, it's the same thing as adding them all together. So log okay, so we're going to take the log instead. And we're going to see why, and it's actually a lot easier to deal with. Okay, so let's just consider one feature for now. Okay, so consider one feature for now. Okay, and for one feature, it's just this, right? It's just the normal Gaussian distribution here. So okay, so if I were to take the log of this, okay, what's going to happen? Well, you can consider this as being multiplied up here. So I can take the log of this guy, the log of this guy are here, subtract it with the log over there. So you would do log exponential, you know, this stuff in here, and then subtract the log of, okay? You consider this as to the power of, you know, power of half. Okay, so if you remember the log probability, you know, the log rule, you can bring the half down here. And because the exponential goes away, this becomes minus x minus y squared divided by 2. Okay, and then this becomes minus half. Okay, and I can split this up even more. Sorry. Can't write today. Okay, and then I can split this up more because this is basically a product between two. So this becomes a half log 2 pi minus, and then the 2 you can bring down there, so it becomes log of, actually no, we'll do log half log squared. Okay, so this is what the log would be. Now, because we're taking this and we're equaling it from one to another, what's going to happen is that you're going to have this constant factor here. When you set this to be equal to another class, so you have this on one side and then you have this term on the other side, they're going to both cancel out when you set them equal to each other. All right, so both It cancels out as this appears on both sides. Okay, so that's what's going to happen. So this cancels, and I'm left with this. So therefore, my discriminant function for one feature is minus okay, and then minus half. Okay, and then you have to add the log probability as well. Okay, so this guy here is log of px, well, probably x given the given the class. That would be the discriminant function here. So therefore, the decision boundary is when you set these both equal to each other. So I'm just going to take this guy here, let's copy it, right here. So this becomes class 1. Okay. So sorry, this becomes 1, 1, 1, and then 1, 1. Okay, equals, and then fine. I'll just rewrite this. Then and then plus. Okay. So sorry, log. So this would be the decision boundary. Then all you have to do is solve for this, and then you're done. Let me just make this a little neater. Okay, so that's how you solve for the decision boundary. Let me just give you a little example so you see what I'm talking about. Okay? Just example for one feature. So, example. Okay, so the example is the following. Let's say I have, actually no, before I do that, let me just do this. So so this here is G1, and this guy here, this guy here is G2. So the decision rule is if G1 is greater than G2, or if you bring 1 on the other side, so if G1x minus G2 was greater than 0, choose class 1, else class 2. Okay, that's the decision rule. All right. Yep. Okay. Good. Okay. Example. So let's say I'm given the following. So let's say I have, this is just for one feature. So let's say I've got the mean for the first class is 2, and the mean for the second class is 6, right? And let's say that the variance of the first class is 2, and the variance of the second class is 1. And let's also assume that the probabilities are equiprobable, so they're both equally likely to be chosen. If you don't know anything about about the situation at hand. Okay, so all I have to do is just take these numbers and plug them into the equation above here. So I just have to take and plug it in. So in this case, you're going to do x minus 2, right? Right, and then 2 sigma, this becomes 4, right? And then, let's see, minus a half log 2, that's what the variance would be, and then plus log of a half. We're going to check to see if this is, we want the decision boundary, right? So, and this is minus x minus 6, and this is 2, minus half log 2, and let's see, and then, no, sorry, my bad. I want, sorry, it's minus a half log 1 because of the variance, and then finally plus log half. Okay, so these two cancel out because they're on one side, and then log of 1 is 0, that cancels out. So what I'm going to do is I'm going to bring this guy over here, okay? So in this case you have x minus 6 squared divided by 2 minus x minus 2 squared divided by 4, and then minus a half log 2 equals 0, okay? So what I'm going to do is I'm going to multiply each side by 4, and the reason why I'm doing this is because I want to get rid of the fraction. So if I do this, and I'm going to skip the math for you, but when you expand this and when you work this out, you're going to get the following, which is x squared minus 20x plus 68 minus 2 log 2. Okay, remember log is the base e, okay? So this is ln actually, but just want to make sure. So now what you want to do now is you want to classify, because this is technically, this is technically g1 of x, and this is technically g2 of x, right? So what I did here, what I computed here was g1 of x minus g2 of x, because I brought the g2 to the other side. So what I'm doing now is I'm going to classify as w1 for x if this guy is greater than 0, and then else choose omega 2 or class 2. Okay, so you can put this into your quadratic formula. This is a, b, and this is c, right? If you remember, it was minus b plus minus, so this is, this is, b squared minus 4ac over 2a, okay? And when you compute this, what you're gonna get, you'll factor this so that it becomes x and then minus 4.2219, and you get x is 15.7881. And you're going to check to see if this is greater than 0. So you have to figure out the values of x that will make sure that this is greater than 0. So if I were to choose x to be greater than 4.2219, what's going to happen is that this guy will be positive, but this guy is going to be negative, okay? So that's not going to work. So if I chose x to be less than 4.2219, what's going to happen is that you're going to get a negative term and a negative term. They both become positive, so that's good. Okay, so both terms are positive. Okay, and similarly, if you were to choose greater than 15.7881, it's the same thing. Okay, so therefore, choose omega 1 if x is less than 4.2219, and if x is greater than 15.7881. So this is just for a single feature. This is what the decision boundary would be. So if you were if you had a set of training examples and you calculated the mean and the standard deviation of variance, and it came out to be these parameters, this is what the decision boundary would be. So you would choose the first class if it's less than 4.2219 or if it's greater than 15.7881. So let me just show you a picture of what this looks like. Here. This is just for one feature. Okay? So this guy over here, this here is omega 1. This is omega 2, and the mean here. So this was the first mean, this is the second mean, right? And then you have a spread of 2, and this is a spread of 1. Okay, and right here is 4.2219. I just focused on, I didn't draw the other one just for brevity, but this is the decision boundary. Okay, that makes sense. So anything less than 4.2219, you would classify it as, class 1. Anything else would be bigger and would be classified as class 2. So I just drew what the what the Gaussian distribution looks like, and then this is what would happen if you were to have this situation. Okay, that's pretty cool. Sorry. So okay, so this is decide class 1. Just want to put this in. 15.7781. Okay, I'm going to do the multivariate case, and then I will finish up with minimum risk, and we're done. And we're done. Okay, but in terms of this, any questions here regarding just this is just one feature? Yes. Well, what'll happen is that it'll come up very slightly, like by minuscule amount. I didn't draw it here, but it'll look like it's the difference between like 0.00001. Like it's really, really, really small. And usually we don't consider that because generating a feature that is very, very, very way out there is considered an outlier, so you kind of ignore it. So that's why we just consider just the 1, because the 15 is actually quite large. It's most likely never going to happen, so you don't really consider it. But I just put it there just in case. But yeah, what you do is you draw, or go up to 15, then you draw another line. And if you were to zoom into the figure, you'll see that one of the curves is actually slightly larger than the other. So if you take a look at this side, you'll see that the orange curve, which belongs to the second class, is larger than the first one, which is why you choose that as, which is why you choose the second class. Okay. So you had a question? Ask the same question? Yeah. So yeah, if you actually, I ignored it because it's an outlier, but it's very unlikely that you'll generate something that is 15, and then if that's the case, yeah, you certainly would. But I just drew just the 1 because you rarely encounter the other one. Okay, yeah.
To know that, like, that it would be an outlier, would you just have to test that?
Yeah, it's what's known as anomaly detection. So what you'd do is you'd get a feature, and then you'd see how far it is away from the mean. If it's like 3 or 4 times away from the mean, then you'd be like, yeah, this is completely garbage, you ignore it. Where that's anomaly detection, we'll cover that at the end of the course. So it's actually used when you're taking a look at credit card transactions. What they do is they take a look at the mean and variance of all the features of the transactions you've made, and then if there's a transaction that is far away from the Gaussian distribution or the probability model of what you purchased, they flag you and say, hey, this is you probably didn't want to buy that $1,000 speaker system, and you only buy like McDonald's meals every day, right? So that's actually what's used in credit card fraud, which is actually pretty cool. Do you have any other questions? Or okay, all right. All right, so we're going to do the multivariate case. I'm going to do minimum risk, and then we're going to finish up. So in the multivariate case, if you recall, we're going to take a look at the log discriminant function, all right? For now. All right, and then what we need to do now is we're going to take the log of the likelihood here. And this is for the multivariate case. It's going to be a little messy, but we got to do it. Actually, what I'm going to do is I'm going to go back up and I'm going to copy and paste that formula because I can't be bothered to write it. Okay, let's just take this guy. Copy. Okay. I didn't want to copy the whole thing, which is nice. Okay, so here, and then, okay, good. All right, log. Okay, so what's going to happen now is it's the same situation as before. So you have something at the top and something at the bottom. So when you take the log of a fraction, it's the same thing as taking the log of the top, subtract the log of the bottom. And the log and the exponentials cancel, so we're left with okay, so that's this guy, and then you subtract with pi, right? And then let's see, so n over 2, that's fine, and then subtract this with log. Okay, so what's going to happen here is you can bring this guy on the bottom, you can bring this over here, and you bring this over here as well. So you get so you have n over 2 log 2 pi, then minus a half log. Okay. So remember, because you're trying to find the decision boundary, so when you equate these both together, what's going to happen is that these two quantities are going to be the same, right? Because you're using a covariance matrix that is shared between the two. So if you were to equate both of these together, you'll see that these both cancel as it appears on both sides, on both sides. Okay, so therefore your discriminant function is going to look like this now. So it becomes minus half this guy, and then you have to add this with your prior. Okay, so this would be the new discriminant function here. Okay, that's great. Okay, good. Okay, so in practice, we usually assume the features are independent. Okay? If the features are independent, what this means is, oh yeah, we can also assume they have the same variance. Why is that? Well, when you do the feature normalization stuff that we talked about in the first lab, when you're normalizing so that it has zero mean and unit variance. So you can actually transform your data set so that every single one of your features has the same variance. That's what you're doing when you're feature normalizing. Every single one of them have a variance of 1 because you're normalizing with the unit variance. So you can, it is possible to make all the features so that you are, they're usually independent and they can also have the same variance when you do the feature normalization, right? So feature normalization. I'm almost done. So I got this, I got a graph to show you, then I'm just going to cover another topic and we're good. Okay, so therefore, the covariance matrix is just a bunch of diagonal entries, and they're all the same variance. Okay, and these are all zeros. Okay? All right. So therefore, you can actually simplify this so that, okay, so we have this, and then we have minus a half inverse. Okay. So if you want to find the inverse of a diagonal matrix, it's really simple. All you have to do is it's just 1 over every single coefficient. So this becomes 1 over 1 over. It's just a property of diagonal matrices. Okay. And then this guy here, sorry, this is also equal to, if you were to just take the sigma on the outside and you multiply by the identity matrix. So this here is what's known as the identity matrix, where it's just a diagonal bunch, it's a diagonal matrix just full of 1s, and everything else is 0. Okay, so this is I is the identity matrix. So you can just factor out this 1 over sigma squared, and you can do that instead. So what will happen now is you get minus a half x minus mu I, and this becomes 1 over sigma squared I. And a property with the identity matrix is that when you take the identity and multiply by another matrix, it's just equal to that itself. So you can actually remove this from the equation, and then you can take this and factor it over here. So now we get x minus mu I transpose. Right? So there's a minus 1 on the outside, 2 over 2 on the outside. Okay? This times, and then plus. So this is the new discriminant. Okay? And then what will happen is I'm just going to use some linear algebra rules. So what will happen here is that if you multiply this out, you'll get x transpose x minus x transpose mu I minus mu I transpose, and then x, and then plus. So this is just expanding it out. So this is what. So I'm just expanding this. So you have x transpose, and then you have multiply this by x. So that's the first one here, and then you do x transpose, multiply by this, and that's what this follows here. So that's what you get. Now what's going to happen is that when you equate these together, when you have one side or the other, you'll notice that this is also constant. This is constant, and it appears on both sides. So you can cancel this as well. Because when you take this guy and you equate it on the other side, then you can certainly remove this. Also, these two are equal, right? Because the dot product between two vectors A transpose B is the same thing as B transpose A. So you can actually set these equal to each other. So in this case, you get minus a half. And then this becomes, let's see here, let's see, minus 2, and we'll just do UI transpose x, that's fine, right? And then plus. Okay? And then finally, we can collect this, so you're gonna get mu I transpose x, okay? And then over, sorry, this is sigma here. Okay, and then plus log, sorry, come on. What happens is that I put my palm down before the pen, so my palm does the actual clicking instead of the pen, which is really annoying. So let's see here, So we have log. And then minus. Yeah, I'll skip the minimum risk stuff. It's not important. At least I don't think so. Okay. So that would be the decision boundary. And then if you actually take a look here, well, you can think of this as, a coefficient of A, or it's a matrix of A, and this would be a matrix of B. So in actuality, this discriminant function is linear. So if you did, here, A transpose X plus B, and remember this is an input vector of features. So it's not just one feature anymore, it's two or more. All right, so it's now linear. So this is a linear. Okay, so now the decision boundary. Yeah, I'll skip the minimum risk stuff. It's not. I don't think we need it here. So the decision boundary is linear. So it's simply equal to this. I'll show you an example, and then we'll go. So therefore, it's just this. Okay, and then plus 1, and then minus 2. Okay, and then this is equal to, not UI, sorry, this is the first class and the second class. 1, right, U transpose X. This is, sorry, we're doing the first class and the second class here. 1, 2, and then the second class. And I'll show you a nice example, and then we'll call it a day. Okay, so this will be the decision boundary now. Okay, so this is the mean feature vector for class 1. Okay, this is the prior probability. This is the mean feature vector for x2. For class 2, no, sorry, not x2, class 2, right? This is prior for class 1, right? This is prior for class 2, right? And we assume that all these share the same variance. Okay, so I'll just make a general note, show an example, and then we will end the class. So however, we may get a situation where situation where we can't assume the variances are all the same. Maybe there's some correlation involved, so we can't assume that the variances are the same. So you have to explicitly solve it, which is a pain in the butt. But. Okay. Therefore, you will need to compute the decision boundary manually. Sorry, not the decision boundary, the discriminant manually. Right, so instead you'd have GI of X, so minus a half. So you'd still use the log stuff, right? So transpose, and this is X, right? And then plus. So you'd have to do this yourself, unfortunately. So you just do this, and then you just set G1 equal to G2 and solve. Okay, I'm going to finish up by showing you one last example, and then we're going to call it a day. All right, so here's an example. Okay, so let's say my mean feature for the first one is 1 and 2. My second one is 5 and 8. Okay, and the variances are the same. So this is, they all share the same variance. It's covariance matrix. And we're also going to assume that the priors are equiprobable. So a half. Okay. So what we're going to do now is we're going to figure out what the decision boundary is and see what it looks like. So in this case, what you're going to do is you're going to plug it into the formula that we had before. So you have mu1, which is 1 and 2, right? You're going to dot this with x1 and x2, right? You divide this by 3, and then you have log of a half minus, and then you have 1, 2, you dot this with 1 and 2 because you're doing ui transpose. Divide this by 2 times sigma, which is 6, okay? And then this is equal to, just go on the next slide, 5, 8, sorry, 5, 8, and then you dot this with x1, x2, divide this by 3, and then plus log of a half, and then minus. So I'm just plugging it into the equation, all right? So, sorry, this should be 1, 2, 5, 8, and then divide this by 6 because you're doing 2 times. Okay, so you can cancel this out here. This cancels, and then what you can do is you can solve for this on both sides, and then what will happen is that when you rearrange and solve for this, you'll get x2 equals minus 2 over 3, x1, and then plus 7, okay? So this means that the decision boundary before I do that, so let me just move this down. What will happen is you'll get minus 4 over 3 x1 minus 2 x2 and then plus 14 equals 0. And then what I did was I rearranged for this, so you get this over here. So okay, so therefore, if minus 4 over 3 x1 minus 2 x2 plus 14 was greater than 0, classify as omega 1, else you classify as class 2. Okay, so when you do that, that's what you get, and then I'll show you what the picture looks like, and then we're going to finish up. Okay, so this is what it looks like here. So what I did was I did 100 features, so 100 examples, 50 from each class, right? So what happens is that it looks like this. So this is class 1. So now this is class 1, this is class 2. So let me just double check. Yeah, okay, good. So let me see here, what was it? We got 1, 2, 5, and 8. Yep, so this is class 1, this is class 2, right? And these are the means, so this is mu1 and mu2. Okay, and this is the decision boundary. So this is x2 equals minus 2 over 3 x1 plus 7. So this is the decision boundary. So you see that there are training examples, and also I drew what the Gaussian distribution looked like. So basically anything on this side here will be classified as the first class, and anything on this side will be classified as the second, and anything on that side will be classified as the first. So there's 50 from each class, and there's your decision boundary. So that's what it will look like. You're not expected to draw this, I just wanted to show you what it looks like. On the midterm or your assignments or whatever, you're just expected to do the one-dimensional case, because the second one's a little harder to visualize and a little harder to implement. So yeah, that's basically what it looks like. Okay, that's it for Bayesian decision theory. So next class, we're going to do a full-blown-up midterm review. So I will cover some solutions to the problems that I've released. Anything that's conceptual, you can just look up in the lecture notes, but anything requiring calculations like gradient descent or logistic regression, I'll do that in class. And then you've got your reading week, and then the week after, we're going to have our midterm. And I made the midterm from 9 to 11 because I don't think anyone wants to come in at 8 a.m. I think 9 a.m. is a little better. You probably want to sleep in a little bit. So the midterm will be 2 hours from 9 to 11. The rooms, I will have to figure out soon. They just allocated the rooms for me. They're going to tell me what rooms the midterm will be in. We might have to split it up into different rooms. I don't know how many people there are, but we'll go from there. So 9 a.m. is your midterm, not 8 a.m. Okay, see it? Take it easy.